All right, so let's look at case three. So case three is more complicated because the node to be removed, well, and actually, the node to be removed has two children. Okay, so we want to get rid of this node, but we can't link this parent to like both of these, right? We need a single replacement node here. So here's the algorithm we use. What we do is we look in the subtree with the root as the node to be removed, and we find the smallest is a poor choice of words probably. We find the least child in the right subtree. Okay, so we're going to look in the right subtree, all of these nodes, and we're going to find the least child, meaning the child that is greater than the node to be removed because it's in the right subtree, but it's less than every other node in the right subtree. The reason why we're looking for this child is because if we put this child up here, every other node in the right subtree will be greater than that child, and so therefore it should be in the right subtree, and that's appropriate. So we're going to look for the least child in the right subtree, and we're going to move it up to here. You may initially be like, well, wait a minute. What if the least child in the right subtree has two children, right? How would we deal with that? Because like we would now be in the same condition we were before. But the least child in the right subtree can't have two children, or else it wouldn't be the least child, right? Because if it has a left child, that left child is less than the node. And so we'd keep looking left. So basically we start in the right subtree and we go left, 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 until there is no left child, and that's the node we're going to stick up here instead. This is how we do the removal. The fact that we do the least child in the right subtree is somewhat arbitrary. Okay, we could do the greatest child in the left subtree, and that would work just as well, right? Those are actually equivalent strategies. We just need to pick one. It doesn't matter which one we pick. Okay, so I'm choosing the least child in the right subtree because that's the diagram in the book, and I don't have to make a new one. All right, so that's what motivated my decision. All right, so let's take a look at this in terms of code. So to review our code from before, or from yesterday, we wrote a while loop that finds the node to be removed and stores a reference to the parent node of the node to be removed. That's what all of this code here does. Okay. We then wrote code for case 1 and 2, which we saw the diagrams for. And so now we're ready to handle case 3. So I'm going to put a comment here just to explain, like, if we get to this part in the code, here's what's going on. And if we get here, neither subtree of the node to be removed is empty, meaning there are two children. And therefore, this is case 3 in terms of the slides. So we've got a couple steps here. Our first step is to find the least element of the right subtree. Looking at this picture, we want to find this node that contains the least element of the right subtree. But in order to remove this, or move this node rather, and stick it up here, we need to know this parent as well. So we need to keep track of the parent of the least node in the right subtree, because we need this reference as well, because this node's left child will now be this node's right child, right? So we're going to have to not only find this node, but keep track of its parent as well. So this requires additional local variable. So let's do that. We're going to have the least parent, the parent of that least node. We're going to set it to be the to be removed node first because it might be that one, right? But we'll update it as we go. We also need to keep track of the least node, which is somewhere in the right subtree. So we'll set it to be removed dot right. Could even just be that node, but that's a good place to start. So again, in terms of our search, we're starting with considering, hey, is this node right here the least node in the right subtree? And if so, the node to be removed is its parent. And if not, we'll keep updating those two local variables as we traverse our tree. All right, so those are the two local variables that we're going to be updating. And we're going to write a little while loop here to find the right thing. So while least.left is not equal to null, meaning in this subtree, there is some node that is less than the node we're currently examining. There's a left child. We will update least parent to least. We'll update least to least.left. When this loop finishes, least will refer to the least node in the right subtree because it will have no left child. Least parent will refer to the parent node of that node, and we are good to go with the whole unlinking stuff. Let's look at the picture again. We could change this link here to refer to here, change this link here to and then, for this node, change its right child to point to here and change its left child to point to here. So we could update all three of these links, okay? But this link to this node is already correct, and this node, left and right children, are already correct. So rather than updating all three of these links, we're simply going to replace this node's data with this node's data. It just makes it easier than trying to update all three of those references. So let's do that first. So at this point, I think it warrants a comment because there's a lot going on here. So we're going to say least refers to the least child in the right subtree. So we're going to just move the data and say to be removed dot data equals least dot data. That's a lot easier than updating all three of those links. We still need to, right now we've moved the data up here, but this node is still linked into here. We need to change the parent's left reference to refer to this node's right child. So we have to do this reroute link part. So let's write the code for that as well. I'm going to say unlink the least child. If least parent equals to be removed, oh yeah, let me point this out, sorry. There's actually two cases here. It looks like I forgot to make the slide for both of them, so I'll talk through them. One case is that the parent of this node is somewhere in this right subtree, and therefore for the parent, we're going to change left to refer to this node's right. But it's also possible that, imagine this entire subtree here, these nodes didn't exist. This node here could be the least child in the right subtree. And if so, its parent is the actual node to be removed. And so if that's the case, we need to update the right child link to refer to this node here instead. Okay, so we do have like two separate cases here. So if the least parent is the node to be removed, it's that latter case. And so we're going to say, oops, least parent dot right equals least dot right. Otherwise, we're in the case like in the diagram, and we'll say least parent dot left equals least dot right. Whew. That's what it takes to remove a node.